how that's going to affect the velocity, both in the x direction and the y direction. So all of these airfoils have little pressure measurements, or pressure holes, where they measure the static pressure. And you know, of course, that the velocity at this point is 0. So this allows you to back calculate the pressure, or the velocity at this point. So what it's going to tell you is the velocity at this point different from this point. And you can see that they're both inside of the laminar boundary layer. So they shouldn't be that different. However, if you look at this one versus this one is completely outside of the boundary layer. So it should be very close to the bulk velocity, right? Okay. Conversely, this airfoil is within the turbulent zone, so it should have a lower velocity. Understand? Okay. For this experiment, you guys need to know Bernoulli's equation. We used it last time in the flow measurement apparatus. And, oh, bless you. This is the part that we're going to be using. If you notice, these 2 points are along the same line, so you don't have to consider the potential mgh. So we know that this pressure right here, this is the static pressure, the velocity is 0. So this term cancels out, and this one is the dynamic pressure, so the velocity term is still here. When you back calculate velocity, you'll then find the bulk velocity using this method, and that's going to use the pivot tube that scales up and down in the top of it. What you need to know is you need to be very careful to have the pivot tube facing the direction of the wind. If it's even a degree or 2 off, it's going to have a little bit of air, and it's going to propagate through your entire system. The second thing on this one, it has a lot of air because the velocity is traveling across a flat plate, and this is inducing vibration. So your calculations or your numbers are going to jump up and down like crazy. So what we're going to do is, well, actually, we can't really do much to get rid of this. So we're just going to have to acknowledge it in our lab report. So for you guys, what I want you to do is do 2 velocities, one around 20 and one around 25. The max velocity that this wind tunnel can produce is around 30. So you can go to 30 and then back off a little bit. And what some groups have been doing is doing one at the max 30 and one at 25. I just want 2 different calculations, so you guys can choose your velocity, because you're going to be guessing. Let me just start out right now. We have no way to actually back calculate velocity, or that will show up on the screen. So you're going to be guessing what the velocity is. Okay, so you're doing 2 velocities, and there's going to be 2 graphs that I want from you. There's going to be a graph of local velocity versus the tapping number, and one for the boundary layer. So again, it's like the graph in the x and y. Oh my gosh, what are they doing? Okay, so it's kind of going to tell you how the velocity is changing along the y of the airfoil versus how it's changing along the x, right? Okay, so, oh, also, quick note on this one. Number 2 is out, so 2 is now 26. I will actually go over there and point that out to you again, just in case that is lost in translation. And I will come over and teach you guys how it works in a second. So if you want, you guys can go over and start reading the lab manual. This one's next. You guys. Okay, so what we're doing with this is we're measuring drag force using 2 different methods. Drag force is the resistance of the body as it moves through a fluid. So we are going to be using a cylinder, which is already in here, so you don't have to change it out. And the first method that we're going to be using to calculate drag force is by balancing a mechanical moment with the hydraulic moment, very similar to what we did in the hydrostatic bench. So we are going to adjust the velocity using this lever right here to have the velocity. And we're again, we don't have the measurement for this, so we're going to have to back calculate it using Bernoulli's. This is your static pressure, this is your dynamic pressure, and using the same principle as right here, that's how you're going to calculate it. On page 41, this goes through the procedure of how to do it. Or it shows where everything is labeled. So be sure to go over that. So that's the first way that you're going to calculate drag. The second way is using this pivot tube and traversing the wake. As you can see, it goes back and forth. Again, this needs to be pointed directly towards the velocity of air, or the incoming air, or else it's going to induce error. Also, since the cylinder is symmetric, you only have to do half the weight, right? Because it's going to be symmetric. So you can do all the way up into the middle and then go back down. You only have to do that once because it's kind of tedious. Whereas for the mechanical moment, you need to repeat it 5 times. For the to-do list, you need to read out the P0 and PE and balance the weight to 5 different velocities. Again, that's using Bernoulli's to calculate your drag. And complete the table that's given. You need to draw a diagram right here and right here. I want the drag force versus the dynamic pressure, and I want the coefficient of drag versus Reynolds. Right? We know how to calculate Reynolds based off of the previous experiment that we've done. And finally, I want the velocity traverse in the wake and okay? And that's basically using this guy. And I want you to do the calculations based on the sample provided in the lab manual and find your coefficient of drag. And that's it for you guys. So you guys can start reading the lab manual if you want to. Okay, for you guys,